Hello, everybody. Hope everybody's excited. So today we are going to talk about automating real-time pipelines. With me I have Basar and Chen. So today our presentation will be divided into the following sections. First, we'll talk about our objectives. We will give you an overview of the frameworks we use at DoorDash. And we'll also talk about the data control plane isolation we have achieved and are working towards, and then go into the automations in place. So we have automations for operations, usability, and reliability. So the real-time pipelines we have help us do the following things. So ingest analytical events, we do change data capture, and we also build real-time features, insights for machine learning use cases. And our focus is on three things: reliability, which means we want to ingest and deliver these events timely and reliably; usability, so we want to make it easy for our customers to onboard to our platform. We want to create as little friction as possible. And we want to take out the operations from it. So we don't want the customers to think about the operations of the pipelines, and we should also make the pipelines we build cost efficient. So it makes sense to build these pipelines and not buy. So our streaming platform is divided into two frameworks. We have a Flink streaming and Spark. And Flink has a true event-driven architecture, allows for sub-second processing. And you have very precise control of state events through low-level APIs. Spark streaming has microbatch, and this we recommend for seconds and minutes processing latency. And this is supported well with compute for data lake and joins of existing tables. And the tooling for this is also very mature. So now, to dive into depth here, so we have data plane and we have control plane. Our data plane is the pipelines themselves, right? It is a movement of data from source to processing, and we write it to the sinks. And our control plane has two components. So we have an onboarding, and we have the controller. So the onboarding is what provisions these pipelines. It's what customers will interact with to create the resources. And it offers a high level of abstraction for customers. And the controller is what takes care of the pipelines once they're created. So we do auto-scaling, we do auto-remediations. All this type of stuff is done by the controller. We have an overview here for you guys to see.
Right. Yeah. All right. Cool. Thanks, Varun. So let me first introduce our data plan at the DoorDash. So the thing I want to introduce first is a Flink streaming framework. So at DoorDash, we leverage Flink, the built-in streaming framework, to do the data ingestion, which basically ingesting all the analytic events coming from DoorDash web and the website, as well as for internal service. So you can imagine every day people log in DoorDash app. This will generate a lot of analytic events. These events related to people view something, search something, add something to cart, and check out item, order is delivery. So all these events will send into our proxy service. So we convert it as Kafka, which is basically the raw events. And then we're building a lot of Flink application to do the validation, transformation, and extraction of this raw data. And then we convert it as a dedicated Kafka topic and send it to Kafka. And also our internal service, we are doing the same similar thing. It basically send into the internal REST proxy service and send into that Kafka directly. The reason for this is that because this is internal service, we have well control of API to send these events, and also we have a standard format to send and serialize these events. And then we link all these Kafka topic using another bunch of Flink apps. It could be our internal info Flink service, which do the transformation. Also could be some customized, SQL-based language-defined job by our application team. They can do any custom logic they want. And then they will output this data to different destinations. It could be hooked up with our data warehouse solution, which we dump the data to S3 first and using Snowpipe, and then integrate with Snowflake, as well as we can write the data as Delta or Iceberg format if you're using our data lake solution. And also it can be either frozen output Kafka again, then you can build in another Flink application or Spark application to consume this data. And we also have the integration with our Chronosphere, which is our internal metric system. This will be integrated with our alerting system as well, so we can build in the real-time metrics so that you can see how many orders check out right now at DoorDash, and also what is the error rate for some page. And also we have integration with the CIDB, which is basically the database we're using to our application. And also we integrate some third-party tool like Amplitude, which we are using to building some fund analysis. So at DoorDash, we are seeing actually a rising use case of streaming framework. So actually, we're seeing a lot of use cases like people are actually trying to use in a hybrid mode. So for example, this is the graph. We're showing up like how we can generate the personalization features. The CockroachDB we're using right now here is basically for serving the features data. And then we're also using Delta Lake to storing all the historical data. And as people are using this data to do aggregation and either further investigation of the data as well. So for generating the personalization feature, for example, we want to generate what is the current Dash Pass of our user. So Dash Pass is basically some DoorDash membership program. So if user subscribe to the Dash Pass, we want actually reflect the change to the user immediately. Like we can give him some promotion, give some discount about this thing. So this thing naturally can be used as Flink because the latency is so important. So we're using Flink to processing the raw events and updating CockroachDB, and then the application can query this data immediately. Meanwhile, we also need to generate some features like what is the client's last 7 days order or last 30 days order? What is the actual last order date? So this kind of data naturally actually will be easy to use in Spark streaming because we want aggregates with some historical data. So our application team is trying to build in this streaming app using Spark, which we are joining with Delta Lake data, and then updating the CockroachDB. So you're seeing like, actually here we are using a hybrid mode, and a lot of application team trying to build in both, building application using both framework, and they're actually adding a lot of actually learning curve for our team. So that basically like people need to understand different streaming framework and need to understand how to develop the code, how to operate this application. So at DoorDash, we're also trying to build in something to help user easy to onboarding to adopting this streaming framework. So we have something called Unified Streaming Framework, which we providing common abstraction layer for user to easily define streaming application. So basically, user onboarding, they just need to define the job config. And then this job config can be run on different runtime environment. It could be on the Spark on the Databricks. It also could be the Spark on the EMR, as well as it could be the Flink job on the Kubernetes. So we already providing common library for user to how to consume the data, like Kafka, Delta, and also we provide a common library for user to easily output the data, like Kafka Delta, CIDB, Redis as well. So this is basically the workflow, how this US Unified Stream Framework works. So whatever user want to onboarding, they just need to define the job. Basically what they did is like they write a YAML file. We also have a UI to create this YAML file as well. So basically you define what is your source, like your Kafka source or whatever Delta source, and then you define what is the output, and you also can define the computer resource, like how many memory, how many CPU, how many port you want it. And also for the actual logic, it's actually based on the DSL. Most likely it's like SQLite. So user can define their business logic using this SQL file to say what is the actual logic they want to execute. So when we submit this job, you can submit to a different runtime environment, and then you will actually go to this same workflow, like the source will keep consuming the data from the Kafka or Delta, which generated by our ingestion pipeline. And it's shared in the same schema registry, which basically the same schema we're using to ingest the data, to doing the serialization and deserialization, and then execute the SQL file provided by the user, and then do the actual transformation, and then output to the different sink, and then to different destination. So with this, we are actually helping our client to easily onboarding and adopting this streaming framework. Okay, so we already covered the data plan. Let's go to the control plan. So one thing I want to mention is the operation automation. So basically, think about like our ingestion pipeline. We have thousands of Flink jobs, which running all the day continuously, ingesting all the data. So, but apparently, all these Flink jobs consuming a lot of resource, which actually not cost efficient. And we want to actually make this efficient according to the traffic change. Because imagine like what the DoorDash are operating, it's naturally like the traffic will be change all the time during the daytime. So you can see this is the graph which showing the DoorDash traffic. So basically it's very low at the light, and it will go to high during the daytime, and around the first peak around the afternoon, and then reach the peakest time around dinner time. So our job, we hope our job can scale basically based on the traffic, so that it can be scaling down, scaling up during according to a traffic change. That's how we want to achieve this, and we want using the auto scaling. We leverage like Flink reactive mode plus the Kubernetes HPA. So basically, the job will be scaling based on the metric like CPU or memory. It will reduce. It will trying to scale up, scaling down based on the traffic growth. So this is the graph which is showing our task manager pod of our Flink jobs based on the traffic change that you are adjusting the pod number. You see that actually the green line is the actual traffic volume. The yellow line is basically the task management pod. So you see that it actually can change dynamically or continuously based on the traffic. So it actually saves a lot of effort to operating these massive Flink jobs, as well as like considering there's some traffic surge during daytime due to some events or due to some promotions. It's actually reducing a lot of operation because like our on-call need to adjusting the resource and scaling up the job accordingly, which is actually impossible for thousands of jobs. So with the automation, it actually saves us a lot of effort. We actually spend a lot of effort to tuning this automation. We actually leverage, the one thing we actually run into is like the pod flapping, because we're using the CPU metrics to adjusting the scaling. The metric definitely is fluctuating all the time. So we run into the pod flapping at the beginning, and we trying to improve it using HPA v2, which has stabilization window to avoid this frequent change. And we, based on our experience, we are trying to tune this job aggressive in scaling up, and also be conservative in the scaling down. Next is basically the impact of this is pretty awesome. Like we actually saving the cost about 25%, and our peak pod count is down about 44%. All right. So basically the HPA is already awesome, but we also still have some issue right now. One thing is like the HPA for large sleeper job is not actually working as spec. I mean, sometimes it's kind of when a job tries to scale down for sleeper job, we still have some issue to recover the job. This is something we are trying to investigate and solve right now with our computing. Another thing is like for the enable HPA for this critical Flink jobs is actually sometimes will have some generally minor issue, I would say. The one thing is like because during the scaling up, scaling down, the job will restart. So this will actually introduce a short of the latency increasing. And also because the job trying to restart, recover from the last checkpoint, so you are causing some duplicate data. This is not ideal for some critical job, which is sensitive to the latency as well as the duplication. So we are still exploring to improve this within KDA. Basically, like we want to have some cron-based scaling based on the traffic pattern. We can generate some traffic prediction based on the ML model, and this will be reducing the frequency of the scaling. And as well as like we're also exploring to not just rely on the compute resource metric like CPU or memory. We're trying to using something like Kafka consumer lag, something like that, which is more reasonable for the streaming processing. All right. Next, I want to pass to Basar to talk about. Yeah.
Thank you. So I'll talk about the usability automations that we have done. So let's start with what were the DoorDash was at around like 2022 before. The onboarding steps were like we used to create a Kafka topic with a PR. There's a Terraform involvement, and there's on top of it there's an intent test running, and users used to like essentially manually create that PR. And on top of it there's like a Flink job configuration. There's a Terraform file for that as well that users have to like or on-call has to create. Then Snowflake table creation, Snowpipe creation, either using JDBC or go to the UI and create those. And that's a manual step for everywhere. So that essentially causes potential of mistakes because people are prone to mistakes and they make a typo or something that essentially delays the event processing. Users will see their data a little bit later. And we went into drawing board and to see what essentially we can do to improve that onboarding to make it easier and streamline this in a nicer way. So the first improvement that we have come up with is the cadence orchestration. So the steps described before is very common for every onboarding on real-time pipelines. There's a repeated pattern there. So when there's a repeated pattern, you can use essentially some tool to orchestrate that. And we were looking for it, and there were some challenges into it, where one of them is the infrastructure, they have errors. Like when you're creating Kafka topic, there can be a Terraform problems, or Atlantis. I was talking about Atlantis. And another thing can be like a two-person maybe creating the same PR without knowing, and there could be merge conflict that just essentially you need to resolve. So that, like all these things added up, there is a need for a fault-tolerant and reliable system that can handle the retries and essentially do these steps in an order automatically. So a bit of history. In 2020, DoorDash adopted the Cadence as an orchestration engine across the board, across the platform level. And in real time, we onboarded in 2022. This essentially made all these steps orchestrated in a Cadence workflow. It has the retries and backups and everything involved. And with this, we were able to onboard 3,000 plus real-time pipelines till now with the Cadence enablement. That actually streamlined a lot of things. Next item is that we have in our mind essentially is like hey, we have now automation, but this is not easy for end user to see where the automation is and where the onboarding step is. And another one is also when onboarding fails in some step, Cadence UI is easy, but also we wanted an easy way to, with one peek, we wanted to understand where the onboarding failed. So we looked at alternatives within the DoorDash, and we found that the Slack integration is a very popular thing, and there's a lot of automations on the Slack that built in the DoorDash. We said like, hey, let's use DoorDash's Slack integration to enable steps on onboarding, and when it's finished, let the user know that onboarding is finished for them so that they can reliably go to the table that they're querying data from and be sure that the table is there, everything is set up for them. The next item on the list is, I was talking about a lot of things, right? Kafka topic creation, Flink job configuration, everything. The Kafka topic automation is a little bit needing an improvement. This is due to the legacy architecture. I'll go over a little bit. Previously, the model is your orchestrator or like end user or whatever it is. It just essentially goes into the GitHub and triggers an API call or manually create this PR. And after that, this PR will trigger Atlantis. That takes some time to process. And after that, then our onboarding automation will call the on-call, ping the on-call to say that, hey, you need to approve this PR. And after the approval, then the trigger of Atlantis apply will happen. That takes some time to take effect and merge. And then after that, our orchestrator service will monitor that state of the PR, and then we go to the next step. This is a long process. This essentially can fail, and retries kick in multiple times because of the merge conflicts or some issue with Atlantis. So what we thought is like, what can we do to improve this? And the next item that we have come up with is using a newer architecture, which is, we call it like essentially gRPC-based endpoint, which is in the infra service gateway. So essentially this gateway will take a gRPC request to create the resources that we want. It essentially handles the deduplication, it handles the retries if there's a failure, it handles the validations of the fields that we pass in, and then the topic creation will be automated because it's just a one call. And it's a sync call, we get a response immediately, but obviously that causes us to understand that like the topic may not be created at that point. If that is the case, then essentially we need to call in a monitoring API to fetch whether the topic has been created successfully, because we need that topic to be there for us to be able to run the Flink job. And we wanted to avoid any delays on this, where the Flink job does not see the Kafka topic because it's like in process of creation. So the next item that people have asked for was we use as essentially in a company schema for event formatting, where like events come in and there's a fixed format. The problem is it also evolves during time, where business needs change and new fields need to be added. And this used to be the case where when there's an update happen, they used to come to our Slack channel where, hey, I have an update on this schema, I need it to be reflected in the table, and our on-call used to update the real-time pipeline, update the Snowflake table and Snowpipe manually. And this is essentially, again, same problem with the onboarding. prone to mistakes. People make a mistake in the snowpipe query, and now your data does not show because it may be string versus string value, some null field handling, something. And in that point, we had thought of like, hey, can we automate this? Because we have in essentially our schema backwards compatibility, so we can definitely automate this. And then what we did essentially is, within the same UI that we have built for onboarding, we enabled a schema update where users can come in and they just can fill out the form, and then they press the submit button, and after that, this essentially do the whole steps that we used to do, but in an automated manner, and handles the error cases very gracefully. And also this also tied to the Slack. So when upgrade is finished, essentially update is finished, we let the user know so that they can see their table have new fields that they're looking for. So I talked about the schema update, but I didn't talk about how the schemas are created. So let me go back on this one. So schemas are very crucial, as I said before, to the structure of events. And we in DoorDash essentially leverage the Proto and Auro schemas. The problem there is for web and mobile developers, the schema creation is very hard to define because they're like working on a different structure and format than a lot of backend services. So this creates an engineering toll on creating these schemas, and also that create a friction on creating this onboarding because it kind of delays their onboarding setup. So to prevent this, we actually came up with a solution where a lot of those mobile and web developers work with a JSON, and they have their own payloads well defined. So what we said, like, hey, can we convert that into a Proto or Auro schema, essentially based on whatever they need? And the answer was like a yes, where we essentially parse this JSON and figure out how the schema is created, and it is automatically creating it with, again, cadence-backed workflow where at the end of the workflow is finished, the schema is there where people can fetch in. So all in all, we essentially offer a self-serving experience. This is the UI for it, and this allows the users to come in and onboard new events if they wanted to. They can create their schema, update their schema, as I talked before. And also even more, which I didn't touch base, but they can claim ownership of their events. Like because there's a cost to everything, and we want the teams to know how much the cost operating of this pipeline, so they can go and visit and see that. And also tag the teams and like owners to those events as well. So that allows us to like triage things, like when there's like a high cost coming in from a pipeline, we can know which team to reach out to in a case. So that's all from my usability perspective, and I'm going to let Varun take back on the reliability automation.
Yeah, so coming back to reliability automations, we can look again at the diagram from the beginning. So here, all of the reliability automations happen after the job is onboarded. So once we have a job, we want to keep it running as healthy as possible, and ideally forever. So to work towards this, we have something called an auto-remediation framework. So this works in 3 big steps. So first, we collect metrics on the job health. Then we use the metrics we collected, which could be logs, application metrics, hardware metrics, or even like logical metrics like trigger intervals and Spark streaming. We analyze these metrics to identify the issue. So maybe the job needs more CPU, or maybe it needs more memory, or it's an issue outside. Once we analyze this issue, we auto-remediate. So we construct an auto-remediation action, and we apply it. Now, yeah, so to explain why auto-remediation is needed, no one likes getting paged, right? I think we've all been paged. And with thousands of jobs running, you can have like tens of pages every day. And we want to work to eliminate these pages. So most errors that happen are retriable errors. They're errors that you can fix with auto-remediation. There'll always be a medium tail of errors that are hard to automate, but these are rare. So we can go after the big chunk of the errors that can be auto-remediated. So here's an example of something we are working on. So for example, we can collect from a job that the trigger interval is lagging, right? So what the user configured for the job is behind what the application is emitting. Now, once we have identified this issue, we can apply an auto-remediation. right? So here, the auto remediation would be to scale up the job. Because the job has not completely failed, we can let the job run in a somewhat of a degraded state for a few minutes before the new hot cluster comes up. And once a new hot cluster comes up, we can atomically switch from the current cluster to the new cluster with more resources, where the job is less likely to run into this error. And yes, and it may be that this thing happens again, but then in that situation, we'll scale up. So other use cases where we can recover this is sometimes for our Spark streaming jobs, we have spot nodes used. Spot nodes are cheaper, but they're available for less time. And if the job is not too critical, we may be okay with running with spot nodes. And since spot nodes are cost efficient, we might want to recover the spot node usage. So it could be that we started the cluster with spot nodes, and they got replaced with more expensive on-demand nodes. And we can periodically restart them in the hope that we get more spot nodes to keep the cost too. And yes, and this will of course also help with performance, right? If the job is not performing well, auto remediation will help improve it. Yeah, so I wanted to conclude by talking about the learnings we had along the way of building this over a few years now. So automations always save on time. You do pay a price initially by investing more time building out automations, but in the long run, it is always in both the developer's best effort and also in the customer's best interest to build automations. And you should think about automations from day one, right? You should see how you expect your platform to grow and what you expect the eventual load to be a little bit down the line and build towards that, right? And customer experience is always important, even if you build everything that works very reliably and is cost efficient. If it's too much toil or if it requires too much domain knowledge for the customer to onboard to your platform, they'll probably think twice before they go with you. So making a self-serve UI, making it easy from a user experience perspective is also important. And cost efficiency. So in our case, we worked on the HPA stuff after building out the pipelines. And this was done retroactively, but looking back, it would have probably been better to start with this from day one. Because when you play catch up, there's also other moving pieces, and it's hard to account for these things. So you'll spend more time building out the automation later on. And yeah, and I wanted to conclude by saying most errors that we have seen have been retriable errors. These are errors that we see over and over again. So having like a framework that has like a log of all these retriable errors and which we retry on will save most of the on-call burden and the operations around it with this. Yeah. All right. So if you guys have any questions, do let us know.
Hi, I had a question about the schema updates. Mm-hmm. How do you handle updates where they are not day forward friendly? So like going from a string column to an integer type, string type to integer type or something like that.
I can explain that. I think a colleague has talked about this, but we have a schema registry as we talked about, and it has actually the CI/CD. During the CI/CD of this schema creation or updating, we essentially check whether this is like backwards compatible or not. So we actually handle that at that level. So we don't fail at the later stage, we fail at the early stage so that people will know what they're doing is right or not.
Yeah, it is when the customer makes the change to the schema, they will get feedback in the UI that says this is not possible.
I think, sorry.
Thank you. So you don't essentially make the schema update, but you just say it is possible or not possible.
Sorry again, can you say again?
Just following up on that question before my question. So you just say that the schema update is not possible or possible? If
right.
It is not,
we, as a company policy, yes, as a company policy, we are very adamant about the schema, essentially backwards incompatible changes are like prevented, like essentially we kind of like don't want to enable that. That kind of like causes a lot of issues, not only our processing, but downstream also. So we want to be sure that we don't like enable that, and we wanted to prevent as much as possible.
Okay. So do you handle Kafka out of orderliness in the Flink processing, and do you detect anything like that for the real-time processing?
Sorry, I couldn't catch again. One more time.
So when the messages go out of order in Kafka Stream, how do you handle that in the Flink processing? Or does it matter for your use
So
case?
for stateless jobs, I don't think it obviously matters because there's no aggregation that you're calculating. But like for stateful jobs, things are a little bit interesting. I think probably you want to talk about that more likely. How do you handle?
So is that the, you're
Out of
talking about
order.
the schema in the stateful job? Are you talking about like?
In the
events.
stateless or
order.
stateful jobs, how do you handle out of orderliness of the messages in the Kafka Stream?
How do you handle out of order events in a Kafka topic?
I see.
That's why I was
see.
thinking it might
I
be
see.
better to talk.
So yeah, we definitely have some latency handling. Basically, for stateful job, you can handle late event, right? We have some special filtering for the late events. So basically, we have some configuration as well. Like for example, you can have how many out of order events, the time gap you can handle. So basically, for each application, we have different configuration. So basically, based on your requirement. For example, we have something called abandon use case. Basically, it's like for example, like when people adding something to cart and then people abandoning the cart, we want to send notification to our clients to remind them about this cart. So that we can set this out of order thing to be pretty low gap of time, probably within like a few 30 seconds, something like that. So that if there's a late event coming, we just drop it. And we want to include it in the safer job. Yeah.
So if the carts are abandoned and if they started but you don't get the abandoned message for whatever reason, how do you deal with it?
So because this notification need to be sent in real time, right? We don't want to be sending, out of order or late notification
Yes.
for our client. So basically for these late events, we basically will we have some gap, for example, like this out of order for 30 seconds. If it's beyond that limit, we will drop it. But if it's within that limit, we still handle it.
Essentially, it's a grace period that it handles.
Yeah.
But after that, we essentially.
Yeah, but we won't actually just, like I said, the drop basically is not really including in the output directly, but it will actually have a side output, which for all these late events, because we don't want losing any events. So this event we can still be using for the further analysis, but it won't be including in the actual real-time application directly, yeah.
So this is regarding reliability and the automation piece that you talked about. So in case of Flink stateful processing, you said, I think Varun said that we are going to kind of get another cluster up before we switch over from the earlier cluster, right?
So that is for Spark. So that is for Spark streaming, so where we do the hot swap. For Flink, we do not do a hot swap.
Okay. My other question is, because in case of managing the capacity, like how do we handle the outage? Because in case of kind of changing the capacity when you have to restart the pipeline, how frequently you do that, and how do you do in case of your state size is very large, because recovery time is
So I think you have two questions, right? So the first question is, if I need more capacity and if I cannot get it, what happens? And the second one was about state. So I can answer the first one.
Yeah, go ahead.
So for this about capacity, compute capacity, we do work with many different cloud providers. So our controller is an abstraction over many different cloud providers. So the customers do not even know which providers that the job needs to run on. So we will check with the many different providers to see which one has the capacity to accept this new job. And we also have some extra nodes on standby for some critical jobs as well, so that critical jobs are never also impacted by any of this.
Right. Can I hear the second part of the question? Sorry, one more time.
So yeah, actually to follow up the answer, because you are saying you are running the pipeline in multiple different cloud providers, right?
That's for Spark, though.
Yeah, so this is Spark.
Not about Flink?
Like multiple providers, no. Flink is like right now only on the AWS essentially.
So you like mentioned about Spark job like tuning. Like, can you explain what signals do you use to tune the Spark jobs?
Yeah. So are you looking at streaming jobs, right, in this presentation? So the main signal that we use is like the trigger interval, right? So how long it takes for it to process these micro batch. The other signals that we are building out is also the hardware resource metrics. So it runs on a cluster. We can get the average CPU usage, memory usage. These could also be other signals. We also consume logs to see if there's some signals in the logs that indicate any error. Because sometimes it also happens that sometimes people might make a mistake and the job might have a syntax error, and it gets submitted with this, right? In that case, the auto remediation would be to like stop the job and not let it run further. So that is also there, yes.
Hi, I think it was for the Flink platform that you guys had the auto scaling. Like, is there always a guarantee that capacity is available when you expect like the traffic to increase?
We actually, that's a good question. Actually, I think this is related to our computer resource, how many we have. So we do have a limit. I mean, if for example, like at least at our computer resource, we cannot scale up beyond some certain numbers. So it's basically they have the maximum limit and the for all the task manager actually. Yeah.
Yeah, but if we are approaching the maximum limit for like a few days, we will know about that ahead of time, right? When we look at it over a month or 2 months, so we can work with our compute team also to increase the limits.
Yeah.
Right. I think the compute limit, from what I know, I can talk a bit more on this one because I have some context. This is a limit that they like compute teams set for not people flooding the infrastructure with the large clusters. It's not like I think a limit due to compute infrastructure. It's like artificially embedded in limit that they put in. And they can actually say like they can increase it, but they need to know is it going to be in good faith or not. Essentially, that's the part. Yeah.
So you talked about multi-cloud implementations of Spark job. So how do you actually manage it? Can you talk about a bit? Because the question is, source is probably, say, consider GCP cloud. And my Spark job is running, I'm checking that Spark job cannot run in GCP. I want to schedule on the AWS cloud. And my sync is probably in a Azure cloud. So how do you manage the latency, or how do you actually decide that where the Spark job should run?
Oh yeah, so I will be more specific here. So all our hardware is on AWS, but we have different vendors, I should say, not exactly cloud provider. So we have Databricks, we also use AWS EMR. So since they're all in the same AWS account, they can all talk to each other, right? The source, if it's like a S3 table, or even if it's a Kafka topic, it's all inside AWS. Now, to answer your question for a Spark streaming job, one job will either fully run in any given time, either it will be running in EMR or it will be running in Databricks. And this is abstracted away from the customer. They can give their preference, but we'll only run it in one of them. And we will try with different providers to see which one has capacity as well.
You mean provider? Provider means different cloud, or?
Provider as in a Spark provider, so Databricks, AWS,
Okay,
EMR.
within the AWS.
Within AWS, right.
Okay.
So you just like piqued my curiosity with the whole Spark thing. Why would you run one in a Spark provider over the other? Like, what are the pros and cons and benefits? Because I see a lot of overlap and struggling to kind of see.
Oh, so you're asking why we would choose like one vendor over the other for a particular job?
Yeah, because in theory you have like similar underlying compute in your AWS account, right?
Yeah, so I mean, both these providers offer like the same abstraction, right? You tell them your drivers, your executors, and they will run it for you. So cost is also an angle, right? So we have found from our experience, when we try running the same job on different providers, sometimes they finish quickly or they perform better in one provider as to the other. It's not always guaranteed there is one Spark provider that is always optimal. So cost is an angle, and this is one reason why we will choose one provider over the other. We try the jobs on different providers as well before.
Thank you.
When you talked about the different cost metrics, is that automated as well? Like, do you experiment with jobs 10% of the time on one and then run it on the other cloud?
Yeah, so we do collect these cost things in an automated way, right? So our controller will keep track of metadata on a job, its cost, its runtime, where it ran, right? And we do run these experiments where we tried with different vendors as well. But of course, we will work with our customers initially. We will let them know we won't just randomly take their job and run it.
Thank you.